In 2013, heavy rain hit Chongqing and triggered a landslide that buried 18 people and destroyed 4 apartment buildings in less than 3 minutes. The slope had been stable for years. Then water found a crack, pressure built behind the retaining wall, and the wall failed. By the time residents heard the rumble, there was no time to evacuate. This was not a remote mountain village. This was inside a major city of 33 million people, and it was not the first time. Between 2000 and 2015, Chongqing recorded more than 70 slope failures in urban areas, killing over 40 people and forcing thousands to relocate. The city sits on hills so steep that some neighborhoods have vertical elevation changes of 300 meters within a single kilometer. Roads stack on top of each other. Buildings connect to streets at different floors. Tunnels cut through ridges. Bridges jump across valleys. This is what happens when you try to build a modern city on terrain that was never meant to hold one. Now take that problem and push it to an extreme. In Yunnan province, there is a city called Yanjin, squeezed into a canyon so narrow that at the tightest point, the buildable strip is only 30 meters wide. That is the width of a small street. Buildings stand on tall concrete stilts because there is no room to step back from the river. When the water rises, it reaches the first floor of structures. When the slope sheds rock, there is nowhere for debris to go except into the city itself. Yanjin stretches for kilometers as a thin vertical line because the canyon allows no other option. More than 400,000 people live in this compressed strip, and the only way to add housing is to build upward. Some residential towers reach 25 stories because horizontal expansion does not exist. This is the real engineering challenge. How do you make unstable slopes safe enough to build on? How do you prevent water from destroying retaining walls? How do you tunnel through rock without collapsing the buildings above? How do you monitor a city that sits on terrain, actively trying to slide, erode, and fail? And how do you do it at a scale that serves millions of people? The answer is not one dramatic project. It is a repeatable system that China has refined over decades. Cut and support, anchor and clamp, bypass and tunnel, and monitor constantly. Every vertical city is built by repeating these moves thousands of times until the mountain behaves like buildable land. Start with the enemy. Gravity pulls everything downhill. On flat ground, that force is absorbed by horizontal friction. On a slope, gravity has a component that acts parallel to the surface, trying to slide soil and rock downward. The steeper the slope, the stronger that force. Add water, and friction drops. Add weight from buildings and roads, and the driving force increases. Add vibration from traffic, and you create dynamic stress that weakens bonds between soil particles. In a mountain city, gravity is not background. It is the active opponent that engineers fight every single day. Before construction starts, survey crews map the terrain in 3 dimensions using LIDAR, drones, and ground-penetrating radar. They are not just mapping the surface. They are mapping underground layers, fracture zones, water flow paths, and weak zones where past landslides have left unstable material. In karst limestone regions like parts of southern China, water disappears into the ground and travels through hidden channels. That means a slope can look dry on the surface while pressurized water moves inside, reducing stability from within. Engineers drill boreholes, extract core samples, and test them in labs to measure shear strength, compressive strength, permeability, and how the material behaves when saturated. For a single slope stabilization project, this can mean drilling 50 to 100 boreholes up to 30 meters deep. On large urban projects, the survey phase alone can take 6 to 12 months and cost millions of dollars. Once the ground is understood, the first construction move is cut and support. You cut into the hillside to create a flat platform for a road or building. But cutting removes material that was holding the slope in place. If you cut and do nothing else, the slope will eventually slide into the new space. That is why retaining walls are everywhere in mountain cities. A retaining wall is not decorative. It is a structure designed to resist hundreds of thousands of tons of lateral pressure from soil and rock trying to move. On steep slopes, these walls can be 15 to 20 meters tall, stepped upward in terraces to reduce load on any single structure. Each terrace includes a drainage layer behind the wall. Without drainage, water pressure builds up and acts like a hydraulic jack, pushing the wall outward until it cracks or tips. Modern retaining systems include weep holes spaced every 2 to 3 meters, gravel backfill layers, and perforated drainage pipes that collect water and direct it away from the structure. In high rainfall regions, drainage is not optional. It is the difference between a wall that lasts decades and a wall that fails in the first heavy storm. Next is anchor and clamp. This is how you force fractured or weak rock to behave like solid rock. Drilling rigs bore holes deep into the slope, often at angles between 15 and 30 degrees from horizontal. Steel tendons or rock bolts are inserted into these holes, and the void is filled with high-pressure grout that locks the steel into the rock. Once the grout cures, hydraulic jacks apply tension to the tendons, creating a clamping force that pins unstable layers back into the stable mass behind them. A single anchor can apply a tensioning force of 300 to 500 kilonewtons. On large projects, hundreds of anchors are installed in a grid pattern. Then steel mesh and concrete facing are applied over the surface to catch small rock falls and distribute stress. This system does not stop the mountain from wanting to move. It creates enough resistance that movement becomes too slow to cause failure. Anchored slopes are checked annually. Tension is measured, and if readings drop, anchors are retensioned or replaced. This is not a one-time fix. It is active management. The third move is bypass and tunnel. In a vertical city, roads that follow the terrain waste time and fuel because they constantly climb and descend. Tunnels cut straight through ridges, keeping routes short and grades manageable. Chongqing has more than 1,500 kilometers of urban tunnels, more than any other city in China. Tunneling is high risk because you are excavating near existing buildings, and you can intersect underground water. If water under pressure breaks into a tunnel, it can flood the heading in minutes and cause ground settlement above. Modern urban tunneling uses controlled methods. Drill small pilot holes ahead of the face to detect water, inject grout to seal fractures before excavation, and install a strong concrete or steel lining immediately after each advance. Tunnel linings are not cosmetic. They are structural shells that prevent the mountain from squeezing the tunnel shut. A typical urban tunnel lining is 40 to 60 centimeters thick, made from high-strength concrete with embedded steel rebar. Expansion joints are placed every 15 to 20 meters to handle thermal movement and ground settlement. Bridges are the fourth essential tool. In a mountain city, bridges do more than cross rivers. They cross elevation. A bridge can connect two ridges at the same level and eliminate a long descent and climb. In Chongqing, some bridges span valleys with drops exceeding 200 meters. These are not simple beam bridges. They are cable-stayed or arch structures designed to carry heavy traffic loads while resisting wind, earthquakes, and temperature cycles. Bridge foundations in steep terrain often require deep drilled piles anchored into rock, sometimes 50 to 80 meters below the surface. Each pile is filled with reinforced concrete and tested for load capacity before the bridge deck is built. Construction time for a major urban mountain bridge can exceed 3 years, and costs can reach $200 million or more. But the payoff is direct. Travel time between neighborhoods drops from hours to minutes, emergency response becomes feasible, and economic activity expands because logistics become reliable. Now, add the human layer. In Chongqing, daily life operates in 3 dimensions. A single building can have street-level entrances on multiple floors because streets exist at different elevations. One famous example is Liziba Station, where a metro line passes directly through a residential building. The train enters on one floor and exits on another because the terrain forced the alignment through the structure instead of around it. This is not a tourist attraction. It is a solution to a geometry problem. The city has limited flat land, and right-of-way is expensive. Threading transit through buildings saves space and keeps routes direct. Pedestrians navigate the city using stairs, escalators, and hillside walkways that connect neighborhoods vertically. Some residential complexes have internal elevators that move people up and down slopes because walking would take too long. This is vertical urbanism in its most literal form. What makes this system survivable long-term is monitoring. A mountain city is never static. Slopes shift millimeters per year, retaining walls settle, drainage systems clog, anchors lose tension. The only question is whether you detect problems early. Modern projects install networks of sensors that measure displacement, tilt, crack width, groundwater pressure, and vibration. Data is collected continuously and analyzed by software that flags abnormal trends. If a slope moves 5 millimeters in a week when it normally moves 1 millimeter per month, that triggers an alert. Crews investigate, add drainage, retention anchors, or restrict traffic until stability is confirmed. In Chongqing, the municipal government operates a citywide monitoring system that tracks more than 800 high-risk slopes. Each site has multiple sensors, and readings are reviewed daily. This system costs tens of millions of dollars annually to maintain, but it has prevented dozens of failures and saved hundreds of lives since it was deployed. Here is why this matters beyond engineering. When tunnels cut through mountains, commute times collapse. A trip that took 90 minutes on service roads can take 15 minutes through a tunnel. That changes labor markets because workers can live farther from jobs. It changes real estate values because remote hillside neighborhoods become accessible. It changes emergency response because ambulances can reach patients in minutes instead of hours. In regions where terrain used to isolate communities, infrastructure turns geography from a barrier into a network. Between 2000 and 2020, Chongqing's urban area expanded by over 60%, and most of that growth happened on previously unbuildable hillsides. That was not possible because land became flatter. It was possible because engineering made steep land functional. Now, return to Yanjin, the extreme case. The canyon city demonstrates what happens when geometry leaves no options. With only 30 meters of width in the narrowest sections, the city cannot spread. It extends as a linear strip for 15 kilometers along the river. Some buildings sit on concrete stilts that rise 8 to 12 meters above the riverbank to handle seasonal flooding. Roads are stacked, a lower road near the river, a mid-level road carved into the slope, and an upper road that uses tunnels and bridges to stay at a consistent elevation. There is no room for parks, no room for wide streets, and no room for sprawl. Every square meter is planned because waste means failure. The city's water supply comes from a treatment plant built on a platform cut into the cliff. Power lines run on towers anchored into rock. Schools and hospitals are multi-story structures designed to maximize vertical space. This is not a utopia. It is survival architecture applied at urban scale. The cost of this system is not small. Building on steep terrain costs 3 to 5 times more per square meter than building on flat land. Retaining walls, anchors, drainage, and monitoring add expense that flat cities never face. But the alternative is worse. Without intervention, mountain regions stay isolated, poverty stays high, young people leave, economic activity stalls. China has consistently chosen to pay the infrastructure cost because the return is long-term development. The investment in Chongqing's urban tunnels, bridges, and slope stabilization between 2000 and 2020 exceeded $50 billion. But the city's GDP grew by more than 400% in that same period, driven largely by improved connectivity and expanded buildable area. This is what a Chinese vertical mountain city really is. Not a concept, not a metaphor. It is a disciplined engineering system that forces unstable ground to behave, redirects water before it becomes destructive, threads transportation through terrain that blocks it, and monitors constantly because the mountain never stops trying to reclaim space. Then it repeats that system across regions where millions of people need to live, work, and move. The result is cities that look impossible but function daily because someone decided that geography is not destiny. It is just another engineering problem with a solution.